So good afternoon, everybody. I think we might as well get started, given that we just have an hour well, we have 2 hours, but given that everybody's time is limited. My name is Ashok Gadgil, and I'm going to give the first of the 3 talks this afternoon. And I am here in Environmental Energy Technologies Division, and I'm also a faculty member in environmental engineering on campus. And before we go much deeper into the question of global issues, I guess it is worthwhile to ask ourselves, why should we care? And why should we bother, okay? So to answer that question, one needs to step back even more. And I want to introduce something that the UN has been developing for some time. It's called the Human Development Index. Some of you might be familiar with this. You can Google this. The UN convened a number of experts to try to develop a quantitative measure, construct a quantitative measure that's a consensus metric of human well-being. And if you actually went to the UN website for HDI, it gives out the formula of how HDI is calculated among different measures from demographic data, which actually have 3 broad areas. Is enlarging people's choice through prosperity, so it is tied to GDP, it's tied to distribution of income disparity, and so on. Long and healthy lives has to do not just with the mortality and the length of life, but also health. So there is issue of expenditure on public health care, number of hospital beds per 10,000 people, and so on. And then acquiring knowledge is also considered really, really important. And that incorporates how many people are literate, how many people remain illiterate, the distribution of literacy and illiteracy across genders, and so on. So the United Nations annually publishes HDI values, and they're published as standard tables. They're posted on the web. You can look them up. The range is 0 is the lowest, 1 is the maximum, and this is all normalized, so it's taken care of. Okay? The reason to start from this background is because I want to give a sense of where everybody else wants to be. And it's a good idea to understand where everybody else is and where everybody else wants to be and how that ties to prosperity, and therefore how does it tie to materials and energy throughput and CO2 emissions. So this is kind of, so you get a sense of historically what is it that's driving people, okay? This map simply indicates HDI 2009. These countries are 0.95 and over, and that's Australia, Western Europe, United States, and Canada. And then it goes all the way down to 0.5 and all the way even to 0.35, and you would see the colors getting warmer and warmer, and some are really, really getting dark. Okay? It gives you a sense of where the world is. Now you can plot this against electricity consumption per capita. Here is the HDI going from 0 to 1. And this is the electricity consumption in kilowatt hours per person per year. This is 0, 5,000, 10,000, 15,000, 20,000. Okay? And as you would kind of spot immediately, the countries with low electricity consumption tend to be with low HDI. We don't find anybody with low electricity consumption having high HDI out here, out there. But this curve goes steeply up and then flattens out. Okay? This is Norway. This is Canada. This is Kuwait. That's United States. Okay? And then you go down. This is Mexico and Brazil. South Africa is here. And you further go down, here is India and Pakistan and Zambia. And this is Niger. Okay? The point being, there is an inevitable, inexorable push from countries with low HDI to move up. And as they move up, inevitably, unless we do something about technological innovation and policy, they're also going to move out in terms of electricity consumption, and that's going to tie to CO2 emissions. Here are CO2 emissions of selected countries. Okay? Now plotted as CO2 emissions per capita in tons of CO2, TCO2, and this is GDP per capita in purchasing power parity, okay? $2,000 equivalent. Okay? Purchasing power parity is a way you make sure that you correct for some of the goods and services being cheaper in a different country than here. So you would say a dollar buys me something here, the same dollar buys me a lot more because of the purchasing power is higher for the dollar. You correct for that, so now you are looking at what's the equivalent income in terms of, so there's parity in PPP. This is a common way to correct for changes in prices of goods and services across countries in $2,000. And you would see India is down here, China is down there and moving up. Brazil is there, this is Mexico, Greece, this is color-coded, so easy to see. South Africa has been there for a while. Russia kind of went down and then started going back up. This is Australia, this is the United States. Okay? This is Japan, Italy, Netherlands. This is Japan, is color-coded down there. This is UK, this is the Netherlands, and this is Germany. The orange dashed line at 5 CO2 per capita per year is the target if we want to stabilize CO2 concentrations at levels that are considered broadly acceptable, which means we have to bring ours and Australians down. We ought to even bring these countries down. And China is already at 5 now this year. India is still at about 2. And the risk is India and China could either follow this development trajectory, or if they got to be energy efficient, they could follow this development trajectory. We don't know which one they will follow, but we know which one they need to follow if the CO2 concentrations are going to remain reasonably low, if global climate change is not going to push about 2 degrees Celsius or we are going to keep to 450 ppm. In terms of carbon intensity of the economy, okay, this is the kilograms of CO2 per US dollar of economy in $2,000. You would notice that China is, USA is only 0.5, China is 2.6, okay? India is 1.7. And this simply reflects the fact that India and China are still building up their infrastructure. They need a lot more steel, they need a lot more concrete, they need a lot more cement. These are all energy intensive aspects of building up their roads and buildings and so on. So it ends up that for $1 of their economy, they need to actually spend a lot more energy and CO2, in addition to being, of course, less efficient for corresponding processes, sometimes, not always. This graph just giving you the landscape of where developing countries stand and where we industrial countries stand, okay? All the industrial countries that contributed substantially to the stock of CO2 in the atmosphere are for short called Annex 1 countries. Okay, there is a whole lot of shorthand in IPCC. So Annex 1 countries have a total of 20% population of the planet, and their emissions are about 50%. And non-Annex 1 countries are 80% of the planet, and their emissions are again about 50%. So if these guys want to become like this, you know where this is going to go. Okay? So that's another way to look at it. Right? A third way to look at it is to remember that average lifetime of CO2 in the atmosphere is on the order of 100 years. So we can ask the question, of all the anthropogenic CO2 in the atmosphere, how much came from us, Annex 1 countries, and how much came from these guys, and non-Annex 1 countries? And that all depends on where you draw the line from which you start accounting. If you went all the way back to 1600s, when European forests had not been totally cleared, then you need to also attribute to Europe their land clearance. They're burning down and clearing their forests for agricultural land. If you drew the line at 1850, when European forests were already gone, turned into agriculture, then European agriculture doesn't show up as a contributor. There's no land use change in Europe anymore. But Brazil continues to show up when they clear their forest. Okay? So there is this debate about where you draw the line in terms of how much anthropogenic CO2 to account for. But generally it is agreed that even if you draw the line at the beginning of the Industrial Revolution, about 80% of the anthropogenic CO2 in the atmosphere, the stock, is from Annex I countries. Okay? Because we already industrialized, primarily using steam power and coal-fired steam power. Okay? So our emissions are about half. This is in terms of the rate of dumping CO2. Our contribution to the stock is about 80%, and we are about 20% of the population. Just giving you a feel for what the balance is. So the question from the developing countries, based on all these data, is of course that the atmosphere is a global commons. A CO2 molecule emitted in the atmosphere doesn't stay above that particular country. It goes all over the world. Okay? So they too argue they need headroom to improve their livelihoods, to get their HDI up. And they have as much right to it as we have here, right? So their question is, they didn't put most of the greenhouse gases that exist today, and they are not the biggest emitters per capita today. So what about us? So if you just Google this whole question called climate change justice, just Google for these 3 words, you would find how much literature there is, both from developing countries and the industrial countries, from people who do philosophy and ethics and law and justice, about what's the right way to share the burden of who should be cleaning up the atmosphere, who should be paying for reducing emissions, who should be paying for keeping a lid on CO2 concentrations. Okay. Here is a IPCC predictions of potential for reductions in CO2 at various prices. Potential for, in terms of, these are gigatons equivalent of CO2, okay, per year reductions. These are at different prices. Prices are 20, 50, and 100 US dollars per gigaton. And these are energy sectors: supply, transport, buildings, industry, agriculture, forestry, and waste. And again, they are color-coded by non-OECD, emerging industrial countries, OECD countries, and world total. The world total color stands for transport, because it's hard to attribute a particular transport to a particular country, because a lot of it could be where, it's just difficult to attribute. So these 3 particular columns for each of these sectors is in terms of US dollars per ton of CO2 equivalent. And you would see that the potential is pretty substantial. I just picked one number of the order of magnitude to just show you what is going on. Today's total emissions are about 30, 40 CO2 gigatons. And this is going forward, okay? So not looking very good. Depends on the price. As the price goes up, the potential for reduction goes up. And error bars are large. But you would see buildings are very large, okay? Buildings, we will have a talk about buildings later on in terms of what is going to happen. The estimates do not include non-technical options such as lifestyle changes. But many people are now beginning to think lifestyle changes are going to be essential. Can't continue the same way and solve the problem we are landing into. This is a slide that shows the efficiency of CO2 production of an economy. So this is kilograms of CO2 equivalent emitted per US dollar of GDP. Okay? It highlights the fact that highly industrial countries, Europe, Japan, Australia, New Zealand, US, Canada, have low carbon emissions or low carbon dioxide emissions per dollar of GDP emitted, okay, per dollar of GDP consumed, compared to the poor economies. Okay? Africa, Latin America are high up there. Just to show some sense both in terms of the structure of the economy and in terms of the embedded efficiencies of the processes in these economies. So it seems that for the developing countries as a whole, improving their human condition, improving their HDI in short, is something that they have a right to, and this is not something we can possibly take away from them. All we can do is offer to see if they can, or help them get to high energy efficiency deployment rapidly. And two orthogonal slices of approaches, multiple pathways to engage in the developing countries, and I'll address some of them or at least illustrate some of them. And also bear in mind that there are multiple economic strata at which these goals need to be addressed. Okay? So the two-pronged approach, which is same for us, we have to decarbonize the energy sources and greatly improve energy efficiency. You saw in Paul's talk different ways to decarbonize carbon sources. Yeah?
I don't understand the words you said on your previous slide.
Okay, good. Thanks for us.
Not what was on the slide, but the words you said. You said we have to help other countries with their energy efficiency, and we have to respect their need to have quality of life. But yesterday's talks were all about there are absolute numbers of gigatons of CO2 that are required, that will cause disaster or will not cause disaster.
Good.
That's not a political question. It's a scientific question.
Good. Good. So,
So, in other words, those kind of things which are political considerations, aren't they meaningless? Aren't they absolutely ducking the point that there has to be a definite target?
so the question is, how do you reconcile the political and physics or the science-based compulsions? Okay?
We have to let everybody improve their efficiency. If China had the best possible efficiency,
I'm time-bound. Let's have this discussion at the end, okay? I just want to go through my slides, and if time permits, we should have that discussion. Otherwise, I'll be happy to talk to you offline. But the question raised is the tension between the physics-based limits, which will drive CO2 too high, leading to catastrophic changes in the climate, versus the political issues of what's ethical, what is just, and how much can we impose on other countries to change or to limit their CO2 emissions. So, decarbonizing energy sources is a much longer term process in terms of whatever innovation we need to do. That will need to go to scale and lead to decarbonizing energy sources on the order of maybe 20 years. Energy efficiency is something we can go to scale on the order of 5 years. We need to do both. There's no doubt about it. We need to start on both right away. It's not that you wait for the first only because it's long yield or long term before the fruits are reached. We have to do that as well, but we must start on both. And in terms of early results, it's going to be energy efficiency, both for the developing countries and for the industrial ones. So multiple pathways, again, very high-level summary. Innovation in technologies to address the desperate needs for the developing countries. Acceleration of demonstration, deployment, and transfer of successful technologies. And here are some examples in front of you. And not just technologies, but also transfer and adapt successful policies to their energy systems, such as demand-side management. And you'll talk a little bit, Marianne will talk a little bit about demand-side management, and I think you might address some. And of course, developing countries have such a wide range of economic strata. There are people who live literally hand to mouth, collect firewood every other day, versus people whose lifestyle already compares to an average affluent country citizen. So which means that different approaches will be needed depending on what kind of lifestyles and CO2 emissions one is addressing. At the top tier, they live like an average affluent country household. air conditioners, refrigerators, cars, electric lighting is common. The bottom of the tier, of course, don't even have electricity, don't have safe drinking water, don't have shelters and health care. So innovations need to be developed to meet their desperate needs because they are the ones who will otherwise follow the traditional trajectory, which has been a high carbon emission trajectory. Okay? Now I would like to go into some illustrative examples just to give you a flavor of what is possible, what can be done. Stoves, and right there I list some potential partner divisions, computational research, material science, ETD. I should have added here our engineering division, with whom I've been working for the Darfur Stoves project, and there's been an extraordinarily valuable contribution from the engineering division too. Okay? So billions of people literally end up cooking on collected fuel wood, collected on their heads, head loads. Okay? This is a photo taken in Africa. Here is another one. And you see, this is not even the kind of fuel wood we are used to. It's not chopped logs. This is twigs. And this is a pretty hard life. Here is a woman. This is actually taken in Darfur. Woman cooking on a 3-stone fire. About 2 billion people, about 1/3 of the world's population, cook on solid fuels, mostly with stoves of very low efficiency. I'll come to that in a second. Mostly in sub-Saharan Africa, most of it cooks just on 3-stone fires, literally 3 stones and a pot that supports. The pot is supported with stones, and that's it. They're only about 5 to 7% efficient. And when I say efficiency here, I mean the fraction of chemical energy of the wood that ends up as heat in the pot. So it's very simple numerator, denominator, very well defined for one cooking cycle. Okay, 5 to 7% of the chemical energy that goes in the wood will end up as heat in the pot here. So it's possible to engineer a more efficient stove. You can do a little bit of training for the cook who tends the fire, and you certainly can improve the stove. At the scale of the problem and the speed with which we are going to do this, we don't have time and room to change fuel wood characteristics, shapes of the pots, and the kind of food being cooked because they are culturally defined. So we must work with some of the parameters which are fixed and some of the parameters which are variable to figure out how can we improve things substantially. In one case, here are fuel efficient, there are several dozen well-designed efficient biomass stoves. Here are 2 metal ones, and here is one made out of cement and stones, and this is one made out of mud and dung. Here is a stove that was developed here at the Berkeley lab, the Berkeley Darfur stove. The weakness in global stoves research has been that world-class engineering science has not been systematically applied to stove designs. People have done ad hoc designs, tried it out, on an amateur scale, and left it at that. Commonly, attention hasn't been paid to user feedback. And because independent field verification of stove performance has been overall missing, the same people who design the stoves and disseminate them kind of go and do surveys and say, yeah, our stoves are doing fine. Which is a deadly mistake because there is always a bias from the guys who develop the stoves to always tell a good story to the funders. So what has happened in the real world is a low-lying fruit again. It's been a not very successful experience so far. About 500 million stoves are in use, okay? And if you can reduce emissions by about a ton per CO2 equivalent per year, we have halfway to a gigaton there. And that's not that's not that difficult to do. Here is a prediction from a paper by V. Ramanathan in Nature Geoscience. Stoves produce black soot, by the way, and black soot is now seen as a very potent driver of global climate change, not only because it deposits on snow and rapidly melts the snow, but also because it directly absorbs sunlight in the atmosphere and warms the atmosphere. So here are this is actually the calculation of all emissions in terms of what is amount of black carbon in the atmosphere over Asia. And this is what would happen if emissions from cooking with wood, crop, or dung were eliminated because of efficient cooking. So you actually burn the carbon off rather than produce black soot. And the cleaning is pretty dramatic between the two pictures. And this is rapid. Unlike CO2, which has a 100-year lifetime, carbon, black soot, stays in the atmosphere only for the matter of 3 or 4 weeks. So this is something with a very early gain in terms of cleaning up the atmosphere of a greenhouse agent. In terms of policy, nothing happens just from technical innovation. You know, this whole story about building a better mousetrap and people building a path to your door doesn't work like that. We all know that. You need something to drive it. It could be market and policy and their interplay between them. So we have a long history in Environmental Energy Technologies Division of working on energy efficiency policy. Current funding is on the order of 10 million, or used to be on the order of 10 million before it shot up. You've seen this graph yesterday in Paul's talk. Formation of ETD at Rosenfeld's leadership, that was in '73. California remains between 7,000 and 8,000 in terms of kilowatt hours per capita, despite a more prosperous economy. And the US, of course, has climbed up and up to beyond 12,000 now. And a lot of it depends not just on technology, but also making sure that policy drives that technology into the market and makes that successful, widely adopted. Okay? ETD has been advising both China and India, and you'll hear a lot about China now in Lynn's talk, to promote energy efficiency in their economies. We have memorandum of understanding with top decision-making bodies in both places, with regular exchanges and advisory visits. So just touching upon buildings, though we'll have a whole talk today about buildings energy efficiency, is the rapid growth in commercial buildings floor area in both India and China. India's growth is expected to be 8.5% per year between now and 2030. China's is currently 7%, expected to slow down to 3%. Chinese commercial buildings floor area already matches that of the United States. And that's still going to grow. India is way, way behind in terms of their commercial buildings floor area. While it also points to the potential for rapid growth on the one hand, which means air conditioning and corresponding CO2 emissions, it also points to the opportunities for doing it far more efficiently than what has been done historically in both these countries. This simply refers to the DOE and California Public Utilities Commission goals to reduce energy consumption in commercial buildings by 2030 by 80 to 90% in all new construction, 50% with retrofits to existing commercial buildings. This is a snapshot just showing you the so-called LEED buildings. Plotted here are the data showing the ratio of measured to design energy use intensity, EUI. It's just a measure of how much energy is used annually in that building per square foot. Okay? So let's leave it at that. It's an awkward British English unit. And this is the design EUI. The key point is as you push the design EUI down, the ratio between the measured to design grows up and up and up till it approaches 3. In other words, it looks good on paper as you design buildings to be more and more efficient towards net zero on paper. But when it goes to measured buildings, they get worse and worse and slip out of our grasp. And that's only because we have not figured out how to do this in a rock-solid, surefire way every time. We have demonstrated in several dozen buildings that it can be done, but that has required very intense efforts from a lot of smart engineers and PhDs sitting around, making sure what went wrong, debugging it, and iterating it. So we haven't gotten to the point of getting all the way down to low EUI and making sure the buildings will work on a scale. And that's where we need to be. And that's where India and China need to be as they build up rapidly. I think I'll let I'll let Marianne talk in more detail about how to approach this. Okay? So from our division, both software and actually people going over have helped in India develop the energy efficiency targets for Indian buildings. So there is some benefit that is coming, but is not anywhere close to what needs to happen. We haven't got our act together fully yet either in terms of the US. And surely the Indians and Chinese need to get there too. You've seen this graph earlier. These are the new US refrigerator use of versus time and retail prices. The size keeps on climbing. The energy efficiency or the energy use keeps on climbing until it drops sharply. Now we are back down here. The green line is the refrigerator price in constant dollars, $1983. And as the standards get announced, you would see that the market actually, the response by more and more efficient refrigerators coming on the market. We now can actually have refrigerators that are down here in Japan already of this size. So we haven't seen the end of this story. We can still squeeze this down. In most developing countries, refrigerators are sold sensitive to first cost, which means you put as little insulation as possible, as inefficient, low-cost motors as possible, as poor gaskets as possible, because that gets you low price, and that sells the refrigerator against the competition. So having refrigerator standards, testing, policy, verification, all of this matters as it did for this country. And we are not there yet in the developing countries either. About China, we have had a very substantial participation from this lab in appliance standard setting process in China, not just in terms of promulgating a standard from here, but helping the Chinese understand the process by which they set the standards. So in many ways, it's the transfer of software and knowledge of how do you set a standard, how you make it happen in your own country. Access to electricity, okay? You would say it's essential for reduced drudgery, improved livelihood. People would do anything for it. Here are two photographs with identical exposure and aperture of a street in Tanzania. This is the street market selling some goods. This is a kerosene lamp which produces about 0.1 lumen per fuel watt. And this is illuminated with LEDs, which produces 30 lumens per electric watt. Okay? Not only is the illumination better, but you see that you are using 100 times less primary energy per lumen when you go from from LEDs to kerosene wick lanterns. 1.6 billion people still lack access to electricity. And this is something they know they need, they know they want, they would do anything to have it. There are people who use even dry cell batteries to use intermittently for flashlights for cooking with in the night. So technological challenges could be as simple as how do you figure out to produce 1 kilowatt hour of electricity per person per day? Okay, remember our number in the electricity consumption was on the order of 10 to 15,000 kilowatt hours per person. The issue is how do you do it affordably and in a way that is robust enough for communities in the developing countries. Okay? A completely separate point would be energy efficient end-use appliances, which would couple with this. You would leapfrog over the high carbon emissions trajectory, which has been a tradition for the first world to arrive where we are now. So we actually conducted a technical and economic analysis of what are the financial implications of how this could be doable and what would be the multilateral lending agencies do to float carbon bonds to make this happen. Is doable is the short answer. Berkeley, and in this case I mean both Berkeley Lab and Berkeley campus, together are tying with India to develop something called RISE. It's a research institute started in India to mirror LBNL's foundry, but the idea is to keep it focused on energy with science, technology, and policy collaboration with Berkeley. Bijli is the initiative launched last year. Professor Ramesh from physics and material science engineering on campus and MSD here, me, Jayant Sate, Shankar Sastry. And the tie-up with RISE is to actually help RISE become the premier energy science and technology institution that's globally competitive. The funding, half of this is already secured from the government of India. The other half is coming from private sector in India. And the idea is to have a tie which works with creating the things that really made a difference out of Berkeley for the energy scene. The next two slides are just about what RISE vision is, because Berkeley had a big hand in helping them think through what an institution would look like. So looking at supply, demand, conversion, efficiency, storage, and transport, and having a long-term vision that looks at science and technology, basic science, particularly partnership with Berkeley National Lab, academia, and policy. So I want to end this slide by showing you this map. And you can kind of begin to see what it represents. It represents human population density. Okay? You already see the high density regions of Asia, relatively sparse regions in the mountain regions here, high densities again in Nigeria and other parts of the world. On a separate slide, here is a map of the world, not a map really, a photograph of the world, a composite of the world, taken from satellites. But so similar image at least. And you would see who wastes more light. This is light going out to the satellites, okay? This is not light reflected from the street back to the satellite. These lights actually leaking out towards outer space. And you would again see high density of light leaking out, but also high density in population of Japan. A lot of eastern seaboard, a lot of Western Europe. Not so much in India, not so much in China. Africa is pretty much unlit. Okay? And you overlay these two slides on each other. And this is what you see. Okay? These guys haven't turned on their lights yet. Most of these guys haven't turned on their lights yet either, nor have most of these guys, right? And when they want to develop, and they want to have electricity, and they want to have prosperity, they are going to be as bright as this. They want to be like this. They want to be like this. They want to be like that. And that comes to the question that you raised from the back about the physics versus the issue of, can we ask somebody else to keep your lights off? Because we want to keep our lights on. Okay? We hope when they turn their lights on, they will turn on highly efficient lights, much better than incandescents, which is what we seem to be shining out there. That's where I want to stop. And we actually have maybe time for one question. Yes, please. Sure. The question is, can I go back to the slide on the HDI?
Wasn't there an enormous range of HDI for the same CO2?
Yes. The question is, isn't there a big range of HDIs for the same CO2 emissions? And the answer is yes. Here we go. Yep. So there is not much of a range in terms of electricity consumption. If your electricity consumption is down, you could be, you're pretty much constrained to be below about 0.6 or 0.7, okay? If you are down here, right? And up there, sure enough, a big range of electricity consumption for the high HDI countries. Is that what you're asking about? Yeah, sure. And it, of course, shows, I mean, Japan is down there, okay? Japan, France, Netherlands, Italy, United Kingdom, Germany, Israel, Republic of Korea is that cluster. And they are doing quite well. Okay, they are about half of per capita electricity consumption compared to United States, which is close to now 15,000, right? Yeah. Yes.
Why is Norway way over here?
Oh, this is electricity, not hydro. It's very cheap hydro. They can export aluminum. It's not CO2, it's just electricity.
Production of electricity, not the consumption of electricity?
No. Even if it is hydro, it doesn't matter. It's not tied to CO2, right?
Right, but it means they're using a lot of electricity.
Yeah.
Electric heat.
They use electric heat. I mean, they have electricity coming out of their ears. Sorry, one more question. Yes.
The slides before this. The slides before this.
This one?
Yeah, this number 5, actually, the value where the origin line is, where this is a target value, right, for our balanced CO2 target value. Is this actually, but we're talking about this will be like 100 years or 50 years down the road to reach this target. Now, is this, but by the time our population may be increased 50% of that, does this include that population factor?
Okay, it's a tough question to answer because this number is itself not a, this is not a very solid firm number. It has uncertainties like what population are you talking at, but you're also asking about what is going to be the time trajectory to reach that 5. Okay, are you going to go up and then come down to 5, or are you going to just stay below 5 and asymptotically approach it for these big population countries, right? So the idea is, if you want to stabilize the atmosphere at some level, you'll eventually have to have the addition to the atmosphere equal to the sink from the atmosphere, right? So this number, I think, is based on current population of the planet. But it's fuzzy because there are error bars here, which I didn't show on this phi number. Okay? But gives you an idea of the scale of the reduction needed compared to where we are. We are at about 22.
Well, this actually vertical value is the per capita. So ultimately, actually, the balance in the atmosphere will be based on the population at that time times the per capita.
Sure.
That's why this,
sure.
this
totally
number is
quite
related
right.
with.
Yeah. Okay, now the rest of the discussion offline. Sorry, I don't want to eat into lunch time. Thank you.